Hi, Michael. Hi, Kai. Good morning. Welcome back. Hi, Faith. Hi, Tristan. Welcome back. Hopefully you're doing well. Hi, John. Hey, Ellen. Welcome back. Hello, Kim. Good morning. Good morning, Joseph. Hey, Zen. Hopefully you're doing well. Hello, Tintin. Hey, Emma. Welcome back. Hello, Santino. Joey G. Welcome back. Hi, Irvin. Good morning. Hello, Jumila. Hey, Bellman. Hello, Jordan. Welcome back. Hi, Ryan. Hi, Nadal. Welcome back. Missed you yesterday. Hi, Nadina. Hey, Wendy. Seem, welcome back. And Micaiah, welcome back. You're doing well. Hey, Leonardo. Good morning. Welcome to the best class of the day. Hi, Frank. Welcome back. Hi, Philip. Good morning. Welcome back. All right. Good morning. Welcome back. I hope you guys are all doing well, and really, I hope you're staying safe as well. I am just looking for Alex. If you're here, please let me know. Greg, Alex, if you're here, please let me know. All right, let's get right to this. The COVID update for today. Here we go. Checking out the COVID update. There's 6,592 cases of COVID in Oneida County. So if you drive around Oneida County, there are 6,592 people affected by the COVID crisis. It's a high number. I guess the good thing is there's 8,330 resolved cases, but that would include the deaths as well. There are 178 people in our local hospital. There's 25 people in our ICU at the hospital and in county. In our, I'm not really sure the difference here. Maybe this is total in the hospital. Maybe this is just from Oneida County. I'm not sure. More news. Let's go. Daily death toll from a couple days ago. It's a tragic number again. There's 7 different families, 7 different people died from COVID 2 days ago. So that's a high number. 7 different families, 7 different brothers, sisters, parents, grandparents, whatever they may be. There's 7 different families, 7 more families impacted by COVID. So that is sad to see that number that high again. So maybe it's someone that you know in this window. Maybe it's not, but don't think you're out of the clear if you don't really know anybody. That's amazing if you don't know anybody, but just be safe. More news about the death toll. 274 people have died from COVID. And I was watching the news this morning, and the national news, NBC News, and another sad stat is yesterday was the highest number of deaths per day for COVID. So since this pandemic began, yesterday's death toll was the highest. That's a sad number to reach. They also said the number of deaths we had yesterday, or it might have been the day before. I'm not sure what day they took the data from, but they said yesterday's death toll was higher than Japan is going to reach all year. The whole country of Japan. Our death toll yesterday in the United States is higher in one day than Japan's going to hit throughout the duration of the year. That's a sad number to report. So be smart, be safe, protect yourself, protect your loved ones. Do all the safety precautions. Wear a mask, social distance. You know the drill. On the other good hand, there's some good news here on this page. There's vaccinations that are now added to the page dashboard. There's 1,127 vaccines that were given out since they started not too long ago, maybe a week ago. So that number, hopefully that increases really quickly. I did get vaccinated yesterday at MVCC. I had my first of 2 vaccines. So this vaccine that hopefully you'll get is 2 different shots. So you're going to get a small dose the first time, and then you get the second of the dose the second time. So hopefully this is the way out from this crisis, this vaccine. It didn't hurt. It was like a flu shot. My arm, it's fine. I don't feel sick. I'm fine. So hopefully that works out. Hopefully they do rapid vaccinations throughout our county to speed up the process so we get back to some traditional normalcy. Our normal life for the last year has been pretty chaotic. This is our normal right now, but once things open up, our normal will change. There's a COVID for today. Hey, Alex, please try to get here a few minutes earlier. All right, moving on forward. Anybody have any questions for me? Anything? All right. All right, see what's going on today. So here we go. Welcome on back. Happy, wacky, wild Wednesday. Quote of the week comes from Dr. Seuss. Quote is, sometimes you'll never know the value of the moment until it becomes a memory. The daily agenda for Wednesday, January 13th, 2021. It's a day 2. Continuing on with chemical bonding, we are going through covalent bonding. We'll start off with a warm-up, which is on unit 2, which is matter. We'll go through another nonpolar covalent bond example. And then we'll talk about the exit pass. And then we'll shift gears, go to polar covalent bonds. Watch a flick, finish up with some notes. Our midterm will be January 26th or 27th, depending on what day it lies. Maybe it's a day 2 where I have all your classes. If you have class on day 2, it'll be this day. But if it's like a day 3, which I didn't go ahead and look it out, scope it out yet. If it's a day 3 on the 26th, then obviously it'll be on the 27th. Please review units 1 through 5 and make sure you start studying so you get the grade they deserve or earn. Attachments are below. Those are what we're going to use for today's class. Please scroll on up to the beginning of our stream for Google Classroom, and you'll see the warm-up for today is listed. Warm up 1:13:21, unit 2, which is going to be matter. So please click on that. This is a Google Forms I switched up from last time. And this is on unit 2, which we talked about at the end of September. So if you want to use your notes, you can. Let me pull up my notes so you can see where we're at. If you want to access your notes, there's a couple ways you could do it. You could go to the Google Classroom, or you could go to this Drive, which again, this stores all your forms, your sheets, your Google Docs. I'm just going to type in unit 2 and hopefully period number 6, 7. There's Kai's. And to refresh from the past, what did we talk about for unit 2 on the 29th we started this unit? We talked about matter. We talked about mixtures, percent air temp, heat and energy. We talked about heating curves, cooling curves, ideal gases, and vapor pressure. This review is only going to be on a few different topics here. This review, I picked a few topics here. Topic 1 and 2. And topic number 5 will be on this review. Topic number 7 will be on the review as well, vapor pressure. The rest of it will come a little bit later for a second review when I go through the units again. So I'll do energy at a later date. So please use your notes. Maybe you don't need to. Maybe you don't want to use your notes. Maybe you want to see what you remember from when we did this portion of the unit. So it's up to you. Oh, there we go. We introduced that there. That's cool. Hopefully not notice. And obviously you can see exactly what we did. So take pride in what you do. Hopefully you have those notes handy. They're still there. Your dog didn't eat your notes. They're right there for you. So you can see this. I will give you 10 minutes to try these 10 questions out. At the end of 10 minutes, we will review them together and see how we did. So please work on this from now till, say, 12:02. So please work on the warm-up now till 12:02. Whatever you put into it is what you get out of it. All right, hopefully enough time to complete that assessment, the warm up here. Let's go over these 10 questions. So feel free to use your notes, maybe not, but let's see how you did for the warm up today. All right, question number 1. Question reads, which equation indicates a process of crystallization? Please put the answer in the chat. Thanks, Kai. Thanks, Faith. Alex, thank you, Zen. Thanks. Dun, dun. All right, as they're rolling on in, thank you for responses. A lot of you guys put D. This curve helps you out. If I think of crystallization, I think of something solidifying. Crystallization, I'm thinking going from a liquid to a solid. So D is the best answer. Checking that out, crystallization, if I look at my curve to the left, it's going, there's crystallization. It's going from a liquid to a solid. So liquid to solid is crystallization. So it has to go towards a solid. A is going to gas, no. B is going to a gas, no. C is going to liquid, no. It looks like D is the best choice. You're going from an aqueous, which means mixed with water, to a solid. So D is the best answer for number 1. Next up, question number 2, it says the energy required to change the unit mass of a solid to a liquid at constant temperature is called, please throw the answer in chat, heat of couple different answers. Thank you. As we're rolling on in, a couple different answers. We are stuck between heat of fusion and heat of vaporization. So for this question, talking about the change, let's highlight this change again. From a solid to a liquid. If I had this question on the regions, I would start off by breaking that up, and I'd figure out a couple, or draw what I could draw from the passage. Figure out what is given to me in the passage. I have a solid, I have a liquid. And when I think of a solid and liquid, talking about a phase change, then I probably would think of maybe a heating curve. There's your heating curve. You have the y-axis, you have the x-axis. And on a heating curve, you have the lowest temperatures on the y-axis, and the time or rate of reactions on the x-axis. You have solids the lowest temp, liquid is in the middle, and then gas is the highest temp. We are looking for a solid to a liquid. So find solid to a liquid, solid, boom, to a liquid. So we're analyzing this transition right there. We did not talk about formation, doesn't sound like much. Combustion's talking about heat or explosion, maybe. Now, heat of vaporization versus heat of fusion. So we have HF and HV. I think the easiest one for students to memorize is heat of vaporization, or me to memorize is vaporization. So vaporize means to evaporate. So vaporization, this curve, happens from a liquid to a gas. This is my heat of vaporization. Here's my fusion. You're putting two things together. You're fusing something together. It's going from a liquid to a solid, or a solid to a liquid is going to be heat of fusion. Choice D is the best answer for that one. D, heat of fusion. Question number 3 wants to know, where is sublimation? What is sublimation? Please put the answer in the chat. A lot of B's, a couple C's. Sublimation. Think of that curve again. Solid, liquid, gas. Sublimation starts with a S. Your phase change goes from a S. It's a long word. It's a big jump. So it starts at the solid. Sublimation starts with an S. It's a long word. It's a big jump all the way up to the gases. So solid to gas, sublimation, solid to gas. Sublimation, solid to gas. Deposition is a gas to a solid. Again, feel free to check out your notes. Solid to gas. Next one up. Which graph shown could represent the uniform cooling of a substance, starting with a gaseous phase and ending with a solid phase? A gas to a solid. Please put the answer in the chat. All right, a lot of answers are B. Excuse me, just coughing there. I had a cereal bar for lunch and it's just like right there. So we're going from a gas to a solid. So gas is a high temp, solid's a low temp. Think about this. A lot of answers. No one picked C. No one picked D. That's good. No one picked C or no one picked D. So I'll get rid of those. If I'm thinking about this question, or if you're thinking about this question, we're going from a gas to a solid. Hopefully you could draw that curve, or at least the axes. We have temp. We have time. It starts off as a gas and ends with the solid. So I would ask you guys, I'm like, okay, it's a gas. Is a gas going to have a low temp or is a gas going to have a high temp? Think about water. If you freeze water, cool water down with a low temp, it's going to be a solid. If you heat up water above 100 degrees, it's going to be a gas. So high temp is a gas. So we have to start high. You have a liquid in between. There's my liquid. And then the solid phase is going to be the lowest temp. So a lot of you guys picked choice B. B is the best one. Gas phase to solid. If you got any of these wrong, you still don't understand my explanation, please feel free to ask. So choice B is correct. Next up, number 5. Kind of gave this away a little bit. A mixture of ice and water is in equilibrium at standard pressure. The temperature of the mixture must be what? So I want to know what temperature we're going to have ice and water. What temperature does water freeze? Please put the answer in the chat. Okay, there's 2 reference points you should definitely be aware of for water. So water heating curve, again, you referring to this thing again, you have a solid at the lowest temp. There's your liquid in the middle. There's your gas up on top. We're trying to figure out this temp right there, the heat of fusion temp, the crystallization temp, the freezing temp. So liquid to solid. A lot of you guys picked, so a lot of you guys picked A. I have a D. So degrees Celsius, the cool thing about degrees Celsius, you have 0 and 100 degrees Celsius. One's going to be the freezing point, one is a boiling point. So this low temp is going to be 0 degrees Celsius. Water freezes at 0 degrees Celsius. Water boils at 100 degrees Celsius. So those two reference points you should definitely be aware of. Water boils, boiling of water happens at 100 degrees Celsius. If it was Fahrenheit, it'd be 212. I threw that up there to screw with you a little bit. And this would be like a Kelvin temp. So 0 Celsius freezes water, and 100, that's when water is going to boil. So that answer, choice B, is wrong. Choice A is the right answer. A is the right answer for number, where are we? Number 5. 5 is A. Someone asked about 4. 4, best answer was B. Okay, just make sure my chat's accurate. Number 6, it wants to know what accounts for the fact that segment CD is longer than AB. Please put in the chat. Problem. All right, so answers are all over the board on this question. Let's check it out. So again, this one's talking about heating curve, solid substance at a constant rate. So we're definitely started off as a solid. So mark it up if you need to. Solid, liquid, gas. From solid to liquid, that is my heat of fusion. From a liquid to gas, that's my heat of vaporization, HV. Boiling point. Boiling occurs at a higher temperature than melting. So it wants to know, why would this segment, why are these two segments I'm circling here have a different, why is one longer than the other? Okay, one's talking about boiling point higher than melting. Kind of, that's not a horrible answer. B is talking about heat of vaporization is greater than heat of fusion. So that looks like it's heat of vaporization. Definitely looks like it's longer than heat of fusion. Choice C is talking about temperature. Average kinetic energy is temperature. The temperature increases at a rate during the boiling point, at a greater rate for boiling than the melting. Temperature is going to be the same. So that is that temp there. The temp there is still going to remain constant. So average kinetic energy is going to be constant at that interval. And when it's going to be freezing, that temperature, whatever that is, it remains constant as well. And then we're not talking about potential energy. We really didn't talk about potential energy much this year. Best answer for this one is going to be choice B. The heat of vaporization is greater than the heat of fusion. Best answer is choice B. Moving on forward, wants to know which one of these represents a physical change. Which one's a physical change or a phase change? Please throw it in the chat. Nice. They're rolling in, and they look like they're the same answers. 6 was B. 6 was B. Okay, several of the same answers, A. So physical change, we're looking for the same phase. So in these examples, something else is given to you, like a kilojoules. That's a form of heat or energy. We did not talk about heat or energy in the form of an equation, but we will eventually. This is going to tell you if it's going to be an exothermic or endothermic reaction. For now, we don't even have to focus in on that heat. So let's not even worry about that. I'll just block it off. Get it out of our lives for now. We'll get into it a little bit later. So a physical change is going to be something that has a physical change is going to be like a change in shape or a change in size, or it could be a phase change as well. So we're looking for a phase change here. Choice A is going from a solid to a liquid. That's a phase change. Looks like a decent answer. Let's look at some more. Choice B is going from a gas to gas to gas. No change in phase. C's going from a gas to gas to gas. No change in phase. Same thing for D. They're all gases there. No changes in the phase. Choice A is the best answer. If they asked what type of reaction is represented by that, they ask what kind of reaction is inside that box. They want to ask it like that, but if they ask you this chemical equation and they said what type of reaction is that, what would you say? What kind of reaction is B? Type of reaction. Is it double replacement, single replacement, substitution? Is it decomposition, synthesis or addition, combustion? So hopefully you could check that out, that equation out, and say, oh, thanks, Jumila. You could check the equation out and say, oh, that is taking one thing plus another thing to make one thing at the end. You're combining them. You're adding them together to make one product. Element plus an element yields a compound. That is synthesis or an addition. So is C. You're taking those two things to make one product. So is D. Taking two things, that plus that, yields one product. So all those examples, B, C, and D, are all addition or synthesis reactions. 7, the best answer though, phase change, physical change is A. 7 is A. Question number 8, talking about vapor pressure. The graph here shows the equilibrium vapor pressure curve of liquids A, B, C, and D. Which liquid has the lowest boiling point? Please put it in the chat. Okay, two different answers I got here were A and D. So vapor pressure comes off from the curve. If you look at vapor pressure, it's going to be in the gas phase or in between liquid and the gas. So heat, so vaporization, that's going to be the boiling portion of the curve. Vapor pressure, if you look in your reference table, we saw vapor pressure, I think it was on page 4. That's the vapor pressure. When we analyzed this, we looked at a couple portions of the curve. We looked at this 101.3, which is standard pressure. We got that from page 1 of the reference table. So let me zoom back to page 1. Standard pressure, 101.3. When I go to page 4, so that means like conditions here on Earth. So at that pressure and whatever the temperature that intersects that line is going to be where water is going to boil. So similar, can't say that word very good. Similar to this graph right here. You have a pressure and you have a temperature. Let's know which one is the lowest boiling point. So we don't have a standard pressure for Tor. So I don't care if you look at either one of these dashed lines, put a random line in between. I'll put one at 380. And I'll say that's standard pressure. If I find the intersection point for each of these lines, you can figure out the boiling point. So nobody put choice B or C. So nobody picked B or C. That's awesome because the ones in the middle are like the oddballs. They're not going to have a low value. It's not going to be high. They're in the middle. So these are not going to be the answer. We're stuck with choice A and D. So get rid of those. So let's find these 2 points. Let's find the intersection points of both of these. If I check out A, if I follow that curve and it hits that line, A is going to have a boiling point of roughly 320. So A's boiling point, we're going to assume is going to be 320 Kelvin. If we check out D's, going through D, follow that line for D, the point where it's going to hit the pink line is going to be where it's going to boil. Hits the line, followed on down, the normal boiling point of D is going to be, I don't know, 395, so maybe 390. 390. Which liquid has the lower boiling point? The lowest temp. Choice A is going to be the best answer. So A is the right answer. Lower temp, lower boiling point. A is the best answer. I hope that helped. Next question. 2 more to go. Number 9, same graph. It wants to know which liquid has the strongest intermolecular force. Intermolecular forces are the attraction between 2 atoms. The higher the boiling point, the greater the intermolecular forces are going to be. So the stronger the intermolecular force, the harder it is to separate those 2 little molecules to make them boil. So the greater the intermolecular force, the greater the boiling point. So whatever one had a higher boiling point is going to have a greater intermolecular force. We just saw that. We said choice D had a higher intermolecular force. So this one is going to be a higher intermolecular force is going to be choice D. Choice D, higher intermolecular force, 390. Number 9 is D. D. And last one right here, let's go through this one. It says, which graph best represents the variation of vapor pressure of water as temperature changes? So again, this is related to vapor pressure again. Please check out page 4 if you need help. Good, Emma, thank you. Yes, this last one, thanks for the responses. C is the best answer. C is the best answer. It looks like page 4 of the reference table. Boom. That looks like choice C. So that could help you out there as well. Somebody asked about question number 9 and intermolecular forces with 320 Kelvin. So no matter what I do, if I look at this question, let me zoom in on this for a second. At 320, yes, the boiling point, 320, let me blow this up. There's my 320 Kelvin. Still, for this one, if you follow this curve, no matter what, temperature, the greater the intermolecular force, it's going to be the lowest pressure. I didn't really word that correctly on that one. So the highest pressure versus low pressure. The low pressure is going to have the highest intermolecular force. That one should have been D. I'll try to find more like that so we can review more like that as well. All right, so that concludes our warm-up. We're done with matter, but I'll probably go back a little bit later to do more review on matter as well. So what's the matter? Done. You don't have to submit it. You do not have to submit that. You could if you'd like to. I am not grading that. The things I grade are my exit passes. I will grade the guided notes, and I also will grade the midterm. So those are the main things that are going to be determining your overall grade for the quarter 2. Warm-up is done. Let's check out guided notes for nonpolar bonds. So please open up your nonpolar bond or your chemical bonding guided notes. Please open those up. We are done talking about ionic bonds. An ionic bond is a metal and a nonmetal transferring electrons. hopefully the more I say this, it's starting to make more sense to you. Ionic bond is a metal and a nonmetal transferring electrons. It's a positive charge and a negative charge. It has an electronegativity greater than 1.7. We talked about binary compounds, ternary compounds. You know how to name them. You know how to make formulas. You know how to write them. Lewis dot diagrams. All that stuff. Covalent bonds are made between two nonmetals. So find covalent bonding. We talked about nonpolar last time. We'll finish it up today. Covalent bonds are between two nonmetals where they share the electrons. They become part of each other. They're closer to each other. The bonds are stronger than an ionic bond. So if these two are sharing electrons, it's going to be pretty tough to steal one away. If someone transfers an electron over, it's easy to just grab one and run with it. If someone's sharing, you and your friend share a cheeseburger, it's going to be tough for someone else to pull it away. But if you transfer a cheeseburger to your friend, as you transfer it on over, someone could pull it right away. So ionic bond versus covalent bonds are closer. Covalent bonds, since they do not have a metal, they do not conduct electricity. They cannot be broken down by dissolving or melting either. Covalent bonds, electronegativity is less than 1.7. If you remember ionic bond, it's greater than 1.7. Anything less than 1.7 is going to be a covalent bond. We talked about number of bonds it could have. We talked about nonpolar representing no pole. NP. Nonpolar, no pole for electrons. It shares them equally or evenly. Nonmetal atoms have a range for nonpolar from 0 to 0.3, and electrons are shared equally. We talked about diatomic molecules. Di means two. Atoms, atomic atoms. Two of the same atoms that bond together are nonpolar molecules. We analyze single bonds, double bonds, triple bonds. Single bonds share one pair of electrons. There's my one pair, or two total. 1, 2. One pair or two total. Double bonds share two pairs, and in a pair there's 2, 4 total electrons. Triple covalent bonds, hopefully you guys know how to make these, you practiced them. There's 3 pairs, or 3 plus 3 gives you 6 total electrons. Yesterday in class, we wrapped up, we went through making Br2, O2, F2, N2, and H2. We did that. Hopefully you guys practice like before class or during your lunch, on a napkin. Hopefully you try to make these diatomic molecules again. We know that these are symmetrical. If you cut them in half, it's the same thing on both sides. So if I took a little stick and cut this thing in half, it's the same thing on both sides. Flip them on over, same. If you take any of these, cut them in half, they're all the same. That is a characteristic for non-polar. They're symmetrical. If you take the electronegativity difference, what's my electronegativity difference for O2? Anybody? Change in En. Change in electronegativity difference. Subtract those two values. Somebody told me it yesterday. So what does that even mean? Let's just talk about it. So it sounds like we're stuck with that one. So if I ask for the electronegativity difference of O2, I would look at page 10 and 11, the reference table. And you could find electronegativity is the attraction for electrons. So let's find O. Let's find electronegativity. There's O. Electronegativity for O is 3.4. If it asks for the electronegativity difference for O2, what would you do? You'd do 3.4 minus the second one of 3.4, and that would give you a difference of 0. They're sharing electrons. The closer you are to 0, the more they're going to share. The further you are, that means someone's going to really hog those electrons. So I don't care if you're looking at O2, I don't care if you're looking at F2, whatever you're looking at here, the electronegativity difference for all of these examples that we did yesterday and the day before were all equal to 0. And that 0 comes into play when you talk about non-polar covalent bonds. If it's going to be in the range from 0 to 0.3, 0 to 0.3 difference for electronegativity is a non-polar covalent bond. So I don't know if I showed you this chart, but what's going to happen is you're going to have this awesome chart that you're going to compile. You'll make it at the end of the unit. And within this chart is going to be the change in electronegativity. So that's going to be change in electronegativity. On this chart, maybe you want to write this to the side, but I'll do it again later. On this chart, you're going to have a couple windows where the first value is going to be of the scale is 0 to 1.3. 0 to 1.3. Rewind. 0 to 0.3, not 1.3. 0 to 0.3. The next window is going to be from 0.3 to 1.7. 1.7, which we'll talk about today. And then the last window is going to be 1.7 and greater. So this is a little range for types of bonds. So 0 to 0.3, the first range is going to be nonpolar covalent. Nonpolar. So nonpolar bonds. The 0.3 to 1.7 is going to be polar covalent. And greater than 1.7, hopefully remember from before, that is going to be ionic bonding. It's a metal and a non-metal. Ionic. A couple other things you should note. So if you subtract these values, you get in the range of 0 to 0.3, it's a nonpolar bond. A couple other things you should know about this is going to be from 0 to 1.7, that window is going to be all covalent. So that whole window is all covalent. So that whole area, from there to there, these are all covalent. Non-polar covalent, polar covalent. We should know covalent bonds are going to be two nonmetals. We should know an ionic bond is going to be a metal plus a nonmetal. I meant to make that pink. We should know a covalent bond are going to be sharing electrons. No matter what, polar or nonpolar, they're still sharing electrons. And ionic bonds, they transfer electrons. And now you can see the electronegativity. So this little chart right here is going to help you identify the types of bonds that you could have in a reaction. So I use this a lot. This will definitely help you out. There's nonpolar covalent, there's polar covalent, and then there's ionic bonds as well. If you take the difference, this will help you out identify what they are. We will definitely do this chart a little bit later too. But there's a little snapshot of what we're looking at. All right, so we looked at the electronegativity difference. Good to go. They're all equal to 0 here. And now we're on to polar covalent bonds. So polar covalent bonds, before I get to the notes, I'm going to play this video. Polar covalent bonds. Enjoy.
Let's look at hydrogen atoms that bond with an oxygen atom. These atoms are sharing electrons, which makes this a covalent bond. But here's the thing. Oxygen has 8 protons in the nucleus, and each hydrogen only has 1 pathetic proton in their nuclei. The ability for oxygen to attract the electrons is stronger than hydrogen's ability. This is known as electronegativity, but I think of it as electron bullying because oxygen is going to have the electrons around its nucleus more often than the hydrogens have the electrons around theirs. As a result, the oxygen side becomes slightly negative and the hydrogens become slightly positive. This is an example of a polar covalent compound. The positive and negative ends create poles, like the ends of a magnet. But not all compounds have this kind of relationship. On the spectrum of bond polarity, non-polar covalent bonds share electrons very equally and don't create poles. Polar covalent bonds share electrons unequally and create dipoles, which also cause some intermolecular attractions. And ionic bonds are so polar that the electrons are actually transferred to the more electronegative element, and their charges attract them to one another, forming an ionic bond. Let's look at some examples of the covalent bonds. Non-polar covalent bonds share electrons equally. Examples include all of the Brinkelhoff twins, like nitrogen and oxygen and fluorine, but also other molecules like carbon dioxide that have atoms with really similar electronegativities. Polar covalent bonds, or just polar bonds, have bonding electrons that are shared unequally, like hydrogen chloride, which is also called hydrochloric acid. The chlorine atom attracts the electrons more than the hydrogen atom, so the chlorine becomes slightly negative and the hydrogen slightly positive. We can symbolize this partial charge with the Greek letter delta. Fluorine gets a partial negative, and hydrogen gets the partial positive. One of the most important polar molecules for life is water. These water molecules prefer to have opposite ends near each other. The slightly negative oxygen ends are near the slightly positive hydrogen end. The polarity of water makes it great at dissolving lots of different substances that are also polar. The water molecules have slight attractions to each other, and even to other molecules. These attractions between molecules are called intermolecular forces, and they are much weaker than either ionic or covalent bonds. But just because they're weaker doesn't mean they aren't important. Intermolecular forces play a big role in determining the state of matter of a substance, like solid, liquid, or gas. The particular intermolecular force between hydrogen atoms that are covalently bonded to a very electronegative atom that is also weakly bonded to another atom's unshared pair or partially negative region of a molecule is called a hydrogen bond. So it's basically the attraction between the partially positive hydrogen to the partially negative region of the atom. In this case, the negative region is oxygen, and that's a hydrogen bond. But bond isn't the best word, because it's so much weaker than an ionic or covalent bond. It has only about 5% of the strength of the average covalent bond, but it's still the word that's commonly used. These hydrogen bonds give water a lot of its unique properties, like its ability to form droplets, or maintain the surface tension when a water strider bug is on it. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe, and follow me on Twitter at...
All right, so polar covalent bonds, metal and a non-metal. So let's check it out. Hopefully you got something out of that video. So polar covalent bonds. There's 2 types of covalent bonds. There's a non-polar covalent bond. So covalent bonds, there's 2 types. There's a non-polar bond, which has no pole. 2 things share electrons equally. So an example would be like Cl2. So I'm going to draw 2 Cls. Cl, Cl. Both these are Cls. Cl has 7 valence electrons. Let's draw the 7 dots in there, 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. This other CL has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. What's going to happen when these two things bond? They're going to share electrons right there, that little attachment. These both have the same size, same mass of 35.5. They're sharing electrons equally or evenly. They're symmetrical. Nonpolar, they're sharing them evenly. Polar covalent bonds, next situation is going to be a little bit different. The polar covalent bonds, let me draw an example. The polar example bond I'm going to give you is going to be HCl. So HCl, this time you have a small little h. Make a small h, hydrogen. And we're going to have a Cl, a bigger, so H has a mass of 1.0. This is going to be bonding with a Cl, which has a mass of like 35.5. So obviously the Cl is the bigger guy here. Cl is going to be taking in electrons, probably. So Cl, HCl. In HCl, Cl we know has, if you look on the reference table, Cl has 7 electrons. 1, 2, 3, 4, 5, 6, 7. And H has, it's in group 1, it has 1 valence electron. So you can see what's going on here. Cl had 7 dots around it. I drew those originally. H had 1. In order to make a stable octet, what happened? That Cl had to gain that 1 electron that it had to Cl. So basically, H donated, Cl would gain the electron. If I take one more electron in, it's going to now have a charge of negative. H donated it, kind of, as a charge of something of positive. So kind of like ionic bonding. So again, this is polar. What's going to happen? If these two things play tug of war, the Cl is going to be a hog and say, give me those electrons. Give me those electrons. He's going to pull that electron over to the Cl. The H is going to be like, I kind of want my electron, but you could take it. And then he's going to pull a little bit to the opposite direction, kind of like a magnet. You have positive pole, negative pole of a magnet. So this Cl, bigger mass, pulls the electron in. So we're talking about polar covalent bonds. Still nonmetals, still sharing electrons, but now someone's being a hog here. So polar covalent bonds, copying our notes down. They're formed between nonmetal atoms. So still nonmetals bonding together. They're still sharing electrons. Nonmetal atoms with an electronegativity difference, this earlier in class, but has an electronegativity difference of 0.3 to 1.7. And again, I will put that little range, that little chart that I did earlier. I'll do that at like the last page of notes. So the difference, when you subtract these values, is going to be from 0.3 to 1.7. What happens here for a polar? One more thing to put in this little first bullet. Polar, if you remember, nonpolar meant no pole. Polar means it has a pole. So has a pole. So something's being a hog. Has a pole. Has pole. Polar, P, is a pole. What's that mean? Someone's pulling the electrons in. Like that Cl, it was pulling those electrons in. Non-polar, NP, meant no pole. Polar, it has a pole. Someone's stealing electrons. The electrons are being shared. The electrons are being shared unevenly or unequally. someone's being a hog and taking those electrons in. How does it work out? The atom with the higher, the more the electronegative element, more electronegative atom, whoever one has a higher electronegativity, will be called something like slightly negative. If you recall, electronegativity, that's the attraction for electrons. The highest electronegative atom was F from the periodic table unit. So electronegativity is the attraction for electrons. The one that has a higher value on page 10 and 11. The one that has a higher electronegativity is slightly negative. It could take in one more electron really easily. The one that has a lower electronegative value is going to be slightly positive charge. So really think about it like ionic bonds. Ionic bonds, one's positive, one's negative. You have metal, you have a non-metal. They transfer electrons. Covalent bonds for polar, one's going to be positive, one's going to be negative, but they're both non-metals. So I gave you the example for HCl. Moving on forward, writing the partial. So this is going to be called partial positive, partial negative. So writing partial could be a little tedious at times. Oops. Partial all the time. Instead of doing that, we could write the Greek letter delta or D, italic D. So it's going to be an undercase letter, lowercase letter. It's a control I with a D. So just an italic D, delta. And that's going to represent partial. So lowercase d, just italic, control I, this little I up here. Control I italics, makes it italic. And to represent partial positive, it's going to be D, control comma positive. I'm just going to italic the whole thing. Now zoom in on it as well, or blow it up. Writing partial negative, very similar. Just going to be a negative sign instead. Partial positive, partial negative. So we're not doing ions. We're not going to draw the brackets. We're not going to draw the positive charge, negative charge like we did for Na and Cl. This time, since it's not an ionic bond, you're not doing the brackets. You're going to cut the brackets, but you're going to put the delta positive, delta negative instead. So we'll practice a few of those. All right, let's try one out. So you want your reference table. Hopefully I'll get through at least one or two of these for today. All right, so the first example we have is HCl. HCl, I drew it for you guys earlier. It's hydrochloric acid. HCl looks that. H is yellow, Cl's green. HCl. There's one valence electron available for H, and Cl has 7. If you have one more electron there, it'll make it stable like that. All holes are filled. Realistically, if this was a model, the Cl would be larger than the H. The masses are larger. All right, so the electronegativity of each atom. So if we check out page 10 and 11, if I look at the electronegativity values for H and Cl, so first one up, H, check it out in the reference table. I'm on page 10 and 11. And let's go through, highlight some of this. Oh, there's my electronegativity. That's the attraction for electrons. There's my H. The electronegativity for H is going to be 2.2. So I have the first value of 2.2, and let's find Cl. Cl. There's Cl. That has electronegativity of 3.2. So two values that we have. You can find those, electronegativity. This stuff's not hard. H has a value of 2.2. Cl has a value of 3.2. Came from the reference table. The electronegativity difference is going to be 2.2 minus 3.2. And if you get a negative value, just turn it to a positive. Not a big deal. So 2.2 minus 3.2 gives us 1.0. So when you subtract them, we get a difference of 1.0. If I think about that 1.0, the electronegativity difference of 1.0, if I look at my notes above, it says the electronegativity difference, if it's 0.3 to 1.7, which 1.0 is right there in the range, wherever it's in between, then it's going to be a polar covalent bond. So once you take the difference, it's going to tell you where it's going to be. Is it polar? Is it non-polar? There's two nonmetals. That difference of 1.0 will tell you it's in that window. Therefore, it's going to be a polar covalent bond. So that's going to tell you it's a polar bond. The partial positive, partial negative, if I scroll above, it says, let's see, the slightly negative, the more electronegative element is slightly negative. So 3.2 is higher, so Cl is going to be partially negative. What am I going to do here? Outside the Cl, I'm going to put control period, should be a superscript. It's going to be control period, control I's italic, delta negative. I'll blow this up in a second. And to the left, it's going to have to be partially positive. The one that's a lower electronegativity value is partially positive. I'll zoom in on this, make this larger so you could actually read it. Partial positive, partial negative should look something similar to that right there. Yes, this is like amazing stuff to know, this partial negative, partial positive. But on the reagents, they will not ask you to identify partial positive or partial negative. Good to know, but don't stress on memorizing this because they're not going to ask you this concept on the reagents. Let's try H and O. Do one more example. H and O. Anybody help me out? What's my electronegativity for H? What's the electronegativity for H? So once we get done with this example, we'll be done for today. I'm gonna ask for like someone in the class to help me out. Thanks. We have 2.2 for H. That came from the reference table to the left, page 10 and 11. So 2.2. How about O's electronegativity? Anybody? Yeah, 3.4. So all we did here, all your classmates did here, is they located them on the reference table. Find H, electronegativity is 2.2, and O has electronegativity of 3.4. A difference of, what is the electronegativity difference from H and O? Thank you. So yeah, 2.2 minus 3.4, got a difference of 1.2. So that 1.2, let's just see what that means right now. That 1.2, oh, it's in the window. It's in that little range of 0.3 and 1.7. So 1.2 is definitely in that window. Therefore, it's going to have to be a polar covalent bond. If it was less than 0.3, it'd be a nonpolar. If it's greater than 1.7, it'd probably be an ionic bond. All right, so we're 1.2. In this situation, the one that has a higher electronegativity takes in electrons easier. So one that has a higher electronegativity, O, is partial negative. O is partial negative. H is partially positive. I'm going to copy the example I have from the last one above. And I'm just going to switch out the O and the Cl for the O. Because it's going to work out the exact same way. The H in the O bond, H is going to be partially positive. The O is partially negative. All right, guys, next time we'll do the O and the N, and we'll do the last two examples there, and we'll move on forward, do some more Lewis dot diagrams as well. All right, so that's going to be it for today. You could do the exit pass on nonpolar covalent bond. It's only 7 questions. Please try it out. That is going to be due on Saturday. I probably will have a polar covalent bond exit pass that will be due on Saturday as well. It's not uploaded yet. I'm going to wait till at least we get through the content before you actually do the assignment. Have a great day. Make good decisions. Be kind to one another. See you later, guys. If you have questions, feel free to hang out. Bye, John. Bye, Alan. Have a good one. Bye, Nadina. See you later. Go for a walk today, guys. Get out there. You'll feel better about yourself if you get some exercise in. I'm not getting my exercise in. Bye, Steve. Bye, Kim. Have a good one. See you later. If anybody has any questions, please feel free to ask. Plenty of time for questions.